Hello and welcome to this small demonstration about the machine learning capabilities of TIMi and Untitled. I am Frank van den Bergen, the CEO of TIMi, and in this video, I'll do a brief demonstration of the machine learning capabilities included in TIMi and Untitled using a small text mining problem. Let's start by creating a new Untitled graph. And import into our graph two tables. The first table contains the text corpus. Here we have a text corpus composed of about 5,000 documents. These documents are about different kinds of investment products available in the stock market. We have documents talking about equity, securities, warrants, etc. Here is an example. All these investment products have one feature in common. They all contain somewhere a number that is named the maximum trading amount, or in other words, the maximum value of one share. The objective of this text mining exercise is to create a solution with TIMi that automatically extracts this number, the maximum trading amount, from the documents. So we have imported in Untitled two tables. The first table is our text corpus with all the documents. This table has two columns, the document ID and the document content. The text content can be quite large, sometimes more than a megabyte. It means that there are some cells inside our table that are larger than 1 megabyte. The second table is a reference table that contains for each document the values that we are searching for. This reference table has been manually created by some humans. As you might have noticed, there are many different numbers in these documents, but which one is the maximum trading amount that we are searching for? To answer this question, we'll create with Untitled the following algorithm. First, extract all the numbers inside the document. Second, create a predictive model that looks at each number and computes the probability that this specific number is the maximum trading amount that we are searching for. Third, for each document, select the number with the highest probability, as computed by the predictive model. This number is the answer that we are searching for. The first point is easy. This is this little box in Untitled. We just specify a regular expression here that matches a number, and Untitled returns a table with all the positions of all the matching strings. As you can see here, there are many numbers inside the document that contains commas. The comma is used as a thousand separator. Let's clean up these numbers by removing the commas. Other numbers are actually coming from dates written everywhere in the document. We can already make a very simple filter that removes all these numbers related to dates. We'll start by removing the numbers in between 900 and 2000 because these are most likely some years inside the date, with the exception of the value 2000 that can still be the maximum trading amount that we are searching for. Let's now have a deeper look at our second table. In technical terms, the second table contains our targets. It contains the exact numbers, the maximum trading amounts, that we must retrieve inside each document. Let's compute some simple statistics about the different value of the maximum trading amount. Let's first count how many times each value appears and plot this information in a bar chart. This bar chart is ugly because it contains too many values. Let's only plot the top 50 values that appear the most often. Inside this bar chart, we see that there are practically no maximum trading amount below 100, with the exception of the value 1. So, to clean up our data a little bit more, we'll include this new information inside our filter. Let's also use our filter to remove all the numbers that start with a 0. To create a predictive model, we need two different things, a target and some features. Let's now talk about the targets. We need to know what is, for each document, the actual value that we are searching for. Luckily, this information is available inside our second table. So we join the two tables, the first table with all the candidate values and the second table with all the targets. We join the two tables using a composite key composed of the document ID and the maximum trading amount. After the join, we see, for example, that inside the document 090045 etc., we are actually searching for the value 1000. And this value is at character position 25041 from the start of the document, so we flag this position as our target. Unfortunately, the value 1000 can also occur inside the same document at another position. The question is, what's the right position? The first one, the second one, or both? This is a very annoying situation where we might flag a position as containing a target, whereas in reality no target was there. Let's look quickly in how much documents such an annoying situation occurs. We see that inside this document here, the target value appears 11 times. Some of these 11 different positions must have nothing to do with the maximum trading amount that we are searching for. So we'll most certainly learn something wrong if we keep this document inside our learning dataset, since we don't have a clean target here. Let's now create a filter that removes from the learning dataset all the suspicious documents where we might learn something wrong. Let's say that the suspicious documents that we must remove are the one where we detected 0 target value or the one where we detected more than 4 target values. Just to know exactly how many documents we are actually removing, I'll add 2 row counters, one before and one after the filter. Let's run the filter. Looking at the counter here, we see that we removed too many documents. There are not even 200,000 rows left inside our learning dataset. Let's modify a little the filter to keep more rows. That's better, we now have a learning dataset with more than 200,000 rows. Let's now talk about feature extractions. To remind you, to create a predictive model, we need 2 different things, a target and some features. We already defined and clean our target. It's this column here in the table. Let's now go back and talk about features. Our predictive model looks at the features to guess if a given number is a target or not. The better our features are, the better the predictive model will be. So we need to find good discriminative features that allow us to separate the bad numbers from the good numbers that we are searching for. For example, if we want to get rid of all the numbers related to dates, we can look at the text located just after the number. If this text starts with a slash sign, it's most likely a date. Our predictive model can easily find such a rule, but since we already know this simple rule, let's code it with Anatella. First, we need to extract the context around each candidate values. What's the text after the candidate value, what's before? Let's first add back the text content inside our table. And thereafter we use the box extract surrounding line to extract the text around each candidate value. This box will actually create two more columns. The first column contains the text before the position of the candidate value, and the second column contains the text after. Now that's interesting. To use the extract surrounding line box, we need one parameter that is a column that contains the length in characters of our candidate value. More precisely, this length is required to know the exact position of the text located after the candidate value. This position is just the sum of the column with the starting position of the candidate value here and the column with the length here. We can easily compute this length using a simple calculator box, but we can't place this calculator box anywhere in the graph. Indeed, this string replace box changes and describes the number of characters inside the candidate values by removing all the commas characters. So we must add our calculator box before the string replace box. We just added a calculator box at the very beginning of our flow. This means that the metadata of our flow just changed because there exists now an additional column named matchedLen that flows throughout all the graph. Thanks to the metadata-free functionality from Untitled, adding or removing a column inside the flow has very little consequences. In our case, it has no consequences at all. But with nearly all other data management tools other than Untitled, what we just did now is terrible. It usually means that you lose half an hour to reparameterize nearly all the boxes inside your data transformation graph down the flow to take into account the fact that your metadata just changed. Very often you lose an even greater amount of time just to reparameterize your boxes. This reparameterization procedure is so painfully slow and cumbersome that many data scientists prefer to avoid using any visual tool for data management, and they go back to old plain and simple code. Luckily, thanks to the metadata-free functionality from Untitled, such painful procedure does not occur when using Untitled. Thanks to the box extract surrounding line, we now have the context around each candidate value. Using this column, we can easily write a filter that removes all the candidate values that are followed by a slash. So let's now go back to our feature extraction work. What could be the features that characterize our candidate values? One idea is to use as features the words located just before and just after the candidate values. Thanks to the extract surrounding line box, we already have these words in the two columns named on same row before and on same row after. As they are, these two columns are not usable inside the predictive model because the predictive model can only use structured text as feature, and these two columns only contain unstructured text. So I will use the bag of word box that transforms an unstructured text to a structured table. Let's apply the bag of word box on the text located just before the candidate value. To structure the text, the bag of word works in this way. It creates a new column for each different words seen in this text column. All these new columns simply contain counter. For example, this one here means that the word fax appeared one time in the text located just before the candidate value. As you can see, the bag of words creates a large number of new columns. We now have more than 4,700 columns inside our dataset. It's very common in text mining to use a bag of word box. This means that in most text mining projects we'll manipulate dataset with a few dozen thousand columns. Untitled is the only tool originally built to handle easily such high column count. Let's apply the same bag of word transformation on the other column that contains the text located just after the candidate value. Maybe it could also be interesting to look at a larger, wider context around each candidate value, because currently the extract surrounding line box only extracts the text located on the same row as the candidate value. Let's also extract now a larger surrounding. Let's extract 3 rows of text before and after each candidate value. And then we structure these 2 larger surroundings using again the bag of word box. We now have some features that characterizes the surrounding of each candidate value pretty well. What other features could we add that could be used to discriminate between the bad numbers and the good numbers that we are searching for? Let's have a look at the numbers that we are searching for. Most of them contain large quantities of zeros. So it might be interesting to add a feature that counts how many zeros there are inside the candidate value. If this number is high, then this candidate value is more likely to be the maximum trading amount that we are searching for. But why stop at counting the number of zeros? Let's look at all the digits. I could use the Anatella's interface to add the other expressions to count all the other digits, but it's easier in this case to edit directly the .anatella file using a simple text editor. This also gives me the opportunity to show you that there is nothing secret or difficult about .anatella files. These are just simple human-readable XML files. So we have now some absolute counts for each digit. Let's also compute the same information, but not anymore in absolute value, but rather in percentage. We can do that very easily using the vectorized calculator. For example, in the number 141001, half of the digits are ones, so we'll have 50% here. Also, the digits used to write the maximum trading amount are not very diverse. Very often, the maximum trading amount is just a number composed of the digit 1 or 5, followed by a variable quantity of 0 digit. Let's compute how many different digits are used to write the maximum trading amount. Let's call this number digit diversity. If the digit diversity of a candidate value is low, then we might have found the maximum trading amount that we are searching for. Let's also compute the digit diversity in percentage rather than in absolute value. Also, amongst the maximum trading amount, the first digit is also very often a 1 or a 5. So it could be interesting to extract the first digit of the candidate values, because if it's a 1 or a 5, we might have found the maximum trading amount. But why stop at looking at only the first digit? Let's also look at the last digit and the last two digits. Okay, I guess that's it. I don't have any more ideas about additional features that I could add to create our predictive model. Let's save everything into a gel file and send everything into TIMi modeler to get a model. But before saving the dataset, I'll remove the 4 columns that contain the unstructured text context because we don't need them anymore. Let's also check the bag of word boxes, just to be sure to use different prefixes for the columns' names, otherwise we might create 2 columns with the same name, which is always bad. That's okay, let's run the data transformation graph to save our learning dataset. That's finished. Let's now have a quick look at our learning dataset. Our learning dataset has more than 33,000 columns and more than 200,000 rows. Let's have a look at the columns' names. Let's now create the predictive model. To create the predictive model, I'll use the simple model factory with less settings. The target column is named target, the primary key column is named ID, the learning dataset is analytical-dataset.gel and we will use performance mode because it's usually the best choice for text mining problems. So TIMi just finished creating the model. As you can see, the model is extremely precise. The AUC of the model is almost 99% on the test set. The number of variables included inside the model is over 1200. Let's have a look at the variables that TIMi selected to create the model. Without too much surprise, we see that TIMi used the variable n0count. It's the quantity of zeros inside the candidate value. Inside this graph, look at the red line. The red line is the probability that this candidate value is actually a target. What do we see? We see that if the quantity of zeros is 3 or more, then the probability to have found a value that is the maximum trading amount is very high. Another interesting variable is percentage digit diversity. As expected, when the diversity is high, the probability to have found the maximum trading amount is low. Here is an interesting variable based on the context. If the word denom is found on the same row just before the candidate value, then there are good chances that this candidate value is actually the maximum trading amount that we are searching for. Here is another interesting variable based on the context. If the candidate value is directly followed by a percentage sign, then the likelihood to find the maximum trading amount is lower. Let's now demonstrate how to use our predictive model in production. For the sake of simplicity, I'll restart from the same dataset that I used to create the predictive model. Inside this dataset, each row is a number extracted from a document. Let's start by using our predictive model to score all the numbers. Our predictive model computes the probability that a given number is the maximum trading amount that we are searching for. For the remaining part of this graph, I'll only need these 4 columns. We designed our predictive model so that the maximum trading amount for a specific document is the number with the highest score inside the document. So let's use the naive deduplicate box to keep for each document only one row, the row with the highest score. For the first document, our machine learning solution tells us that the maximum trading amount that we are searching for is 5,000. And we can verify that it's indeed true because the target column is 1 on the first row. For the fifth document, our machine learning solution tells us that the maximum trading amount is 10,007. But it made a mistake because the target column is false on this row. Let's compute the accuracy of our machine learning solution. The accuracy is the average of the column target, after replacing all the nulls with some zeros. Our machine learning solution has an accuracy of over 97%. Out of the 3,700 documents inside our text corpus, we managed to find the right value of the maximum trading amount 3,603 times. This concludes our very brief demonstration of some of the text mining capabilities of TIMi and Untitled. I hope you enjoyed the ride. See you!